All right, welcome to section 3.3 properties of logarithms. Today we're going to be talking about a few properties that are going to be very helpful in manipulating and changing expressions involving logarithmic functions. Okay, so any kind of expression that includes a logarithm, we're going to learn how to rewrite that or simplify it in ways that are helpful to us, that enable us to solve equations or to draw more information from those expressions. Okay, so just much like any kind of algebraic expression, we can use the distributive property, or we can factor and do things like that to change the way that those expressions look, so that we can ascertain information from those. We could do the same thing with logarithms using a select set of properties. One of the first properties that I want to talk about is the change of base formula, and this is that property that's going to allow us to evaluate logarithms of bases other than e and 10 in our calculator. So if we look at the change of base formula here, essentially what we're doing is we're taking a logarithm with a base of a, and we're changing it to whatever base we would like it to be. So you see here on the right hand side of this particular equation here, they changed from base a to base b simply by rewriting it as log base b of x over log base b of a. So the x ends up in a logarithm in the top, and the base of your original logarithm ends up in a log in the denominator of this quotient. Okay, and I'm going to go ahead and demonstrate that. You can kind of see here where in under the base 10 they changed log base a to base 10, and here they changed it to a base e, and that is handy because again our calculator can only operate in base 10 or base e. So we need to be able to use the change of base formula to get to one of those two bases if we're gonna be able to use our calculator to evaluate those logarithms. Okay, so I'll do a couple of examples here for you. We're looking at log base 6 of 50. Well, according to the change of base formula, what I would like to do is either change this to base 10 or base e. So I'm going to do both because it really doesn't take that long. So I'm going to say, well, log base 6 of 50, according to change of base, is the same thing as the natural log of 50 over the natural log of 6. So notice the 50 ended up in my natural log up here, and my 6 ended up in the natural log over here. Okay, I could change it to base 10 if I wanted to. So natural log of 50 over natural log of 6 is the same thing as log of 50 over the log of 6. And either one of those expressions will get you a decimal approximation in your calculator for the log base 6 of 50. So let's take a look at our calculator and see what happens here. So I'm going to do natural log of 50, and I'm going to divide that by the natural log of 6. Okay, so you'll notice I hit enter, and there we go. We get 2.1833. And if I wanted to change it to base 10, I could. So I told you before that the log of 50 divided by the log of 6 would get me the same thing. And sure enough, it does. You see we get 2.18 no matter what base we switch to. Okay, so there's a quick demonstration of how to use that change of base formula. I'll do it one more time here in example number 2. We're looking at log base 4 of 8, so I can rewrite that as the natural log of 8 over the natural log of 4. So remember, what's inside of the log goes to the top. The base of your original log goes into a new log in the denominator. Okay, or if I wanted this in base 10, I could also write this as log 8 over log 4. Okay, and we'll test that in our calculator. So natural log of 8 divided by natural log of 4, and I hit enter, and there I go. I get 1.5, and I could do the same thing with base 10. So log of 8 divided by the log of 4, and enter, and sure enough I get 1.5. So either one, and you can pick whatever base you want to go to. You can go to base e, or you can go to base 10 when you go to evaluate those in your calculator. It's completely up to you. Okay, all right, so that's change of base. Let's take a look at some other properties of logarithms that allow us to rewrite certain expressions. We have all of the properties right here. The three main properties that I want to cover are inside of the box here: the product property, the quotient property, and the power properties. So if you ever want to reference these notes later on, they're all in one convenient place right there. I'm going to go through each of these properties, show you a couple of examples of each one, and explain what they do to you. Okay. So let's take a look at the first one here, the product property. Okay, and essentially what the product property says is that if I have a product of two numbers inside of my log, that I can split that up into two separate logs that are being added together. And make sure you keep in mind that the bases have got to be the same when we do this. Okay, so we have log base a of u plus log base a of v is equal to the log base a of u times v. So when we see a product of two numbers inside of a log, we can split that up into a sum of two logs. All right, and that kind of makes sense because if you think about your properties of exponents that you learned about back in Algebra 2, when we have two exponentials being multiplied together with the same base, we add the exponents, right? And since a logarithm is just an exponent, we would expect to do the same thing with two logs, right? So if we have two numbers being multiplied together there, we multiply the exponents. So let's take a look here at example number one. For instance, I can take the natural log of 6 and I can rewrite that as the natural log of 2 times 3, right? Because 2 times 3 is 6. So there we go. We have a product of two numbers inside of a log, and I can split that up. So I can rewrite this as the natural log of 2 plus the natural log of 3. Oops, typo. Okay, let's test it out. Let's see if that property actually works. So we can test this one in our calculator here. So I'm gonna clear that out, and let's just real quick, let's do the natural log of 6 and hit enter. And there we go. So there's the natural log of 6. And I said that was equivalent to the natural log of 2 plus the natural log of 3. Okay, so natural log of 2 plus the natural log of 3. And I'm going to hit enter. And sure enough, I get the same exact thing. Okay, so you can see that property working in action. All right, we'll take a look here at one more example of the product property. This is log base 4 of 5x. So we don't know what x is, but x represents a number. So we still have a product of two numbers there. So I'm seeing log base 4 of 5 times some number x. And according to the product property, I can rewrite that as log base 4 of 5 plus log base 4 of x. Easy as that. Okay. All right, the next property that we want to talk about is the quotient property. Okay, so this property helps us with log expressions that have quotients inside of the log. So if I have one number being divided by another number inside of a logarithm, I can express that as a difference of two logs. So log base a of u divided by v, I'm going to put parentheses around that uv, can be rewritten as log base a of u minus log base a of v. Okay, and that kind of makes sense. Again, it ties back to our exponential properties. If you think about it, if I have two exponentials with the same base, and I divide those two, we combine them by subtracting the exponents, right? So a to the x over a to the y is equal to a to the x minus y. So again, a logarithm is just an exponent. So the properties really tie together here. They're very similar to what we did with exponents. So you can remember the logarithm properties the same way that you did with the exponential properties that you learned back in Algebra 2. Okay, so let's take a look at an example here. Natural log of 2 divided by 27. Okay, so the 2 over 27, that entire number is inside of the natural log. So I can actually rewrite this as the natural log of 2, right? So that the numerator here is going to come first, minus the natural log of 27. So the 2 is going to come first, the 27 comes next, and this expression is equivalent to what we saw in number 1. And I'll demonstrate that again with the calculator here. So the natural log of 2 divided by 27 gets me negative 2.602. So I'm going to re-enter that in my new format that I have here using the quotient property. So I'm going to hit natural log of 2 minus natural log of 27, and I should get the same thing. and sure enough I do. I get negative 2.602. So you can see that that property is working for us. Okay, we'll do one more here. Number 2, we have log base 5 of 5 over x. So this works with algebraic expressions and logs as well. So I can actually rewrite this as log base 5 of 5 minus log base 5 of x using that quotient property. Now make sure you pay attention because sometimes in these problems when you apply one property it leads you to the ability to do something else as well. So notice here that we have a log base 5 of 5, and the reason that's important is because that's something that we can evaluate. We can evaluate the log base 5 of 5. If you recall, the log base 5 of 5 is going to be equal to some number. We can say 5 to whatever that number is going to be 5, right? So 5 raised to whatever question mark is equal to 5. Well, then question mark has to be 1, right? So we can rewrite our expression as 1 minus log base 5 of x. And this would be probably the most helpful form of that log. Okay. Okay, the next property is called the power property, and this one relates to a power raised to a power. So you might recall back in Algebra 2 when we talked about exponents, if we have a power raised to a power here, so we have a to the x to the y, we would multiply together those exponents. Well, the power property with logarithms essentially allows us to take this exponent inside of the log and bring it out front, which kind of makes sense, right? Because n is an exponent, and so is this logarithm, right? A logarithm is nothing but an exponent. So we're multiplying together exponents, which is what we did in our exponential property. So they kind of tie together. So let's take a look at an example here with number 1. So you'll notice here inside of the log we have a radical. And remember, a radical is nothing more than a fractional exponent. It's more handy when you're dealing with logarithms to be an exponential or to be in an exponent form versus a radical form. So I'm going to rewrite this as log base 5, and then inside of that log, rather than having the cubed root of 5, I'm going to say 5 to the 1/3. And that's their equivalent. Saying 5 to the 1/3 is the same thing as saying the cubed root of 5. Okay. Now, if I apply the power property, I can take this exponent of 1/3 and bring it out front of the logarithm. So now I can rewrite this as 1/3 times log base 5 of 5. And if you recall, the log base 5 of 5 is 1, right? So this is actually just 1/3 times 1, which is 1/3, right? So this and this are equivalent, right? So log base 5 of the cubed root of 5 is equal to 1/3. Okay, let's try it again here in example number 2. We have the natural log of e to the x. Okay, so don't forget that the natural log of e, or when we say natural log, it's the same thing as saying log base e of whatever, right? Because it's a unique annotation. Okay, now the power property tells me that I can take this x and I can bring it out front. So I can actually rewrite this as x times the natural log of e. You might think you're done, but not quite. Okay, what I want you guys to remember that sometimes there's a little bit more simplifying that you can do at the end of some of these problems. Okay, I want you to focus in on this natural log of e and think about what that says. Okay, so I'm just going to draw an arrow down here. We're just going to focus on that part for right now. The natural log of e is the same thing as saying log base e of e, right? And that equals some number, right? So e raised to whatever that number is must equal e, right? So e to question mark equals e. Well, it should be pretty clear that question mark has to be 1, right? E raised to the first is e, right? So question mark equals 1. So everything inside of that red box is just 1. So x times 1 equals x, and that's our answer, right? So the natural log of e to the x is simply x. Okay. Now, the problems do get a bit more complicated when we combine some of these properties, right? So we can combine the quotient property and the product property and the power property all into one problem and use them in conjunction with each other to simplify expressions. You're going to see one of two types of problems when it comes to this particular topic. You're going to see instructions that say expand. You're going to see expressions that say condense. Okay, so when they say expand, what we want to do is we want to split this up, make the expression as big as possible. Okay, and when we say condense, we want to compact it as much as we possibly can. So we want to make it as small and tight as possible. All right, so when we say expand, we're going to go ahead and take a look here at number one. I see the natural log of x times y times z raised to the second power. So I see a product of three different numbers inside of that natural log, which instantly tells me that I'm probably going to use the product property here. Okay, so I'm just going to write that down. I'm going to go ahead and apply the product property. Okay. And the product property tells me that I can rewrite that natural log as the sum of three natural logs. So I have three numbers being multiplied. So I'm going to say the natural log of x plus the natural log of y plus the natural log of z raised to the second power. Okay. And I can expand a little bit more even, because notice on this natural log of z down here, on this part of the equation, I have a 2 in the exponent. Okay. Using the power property, I can pull that 2 out front. So I'm going to go ahead and apply the power property, and I'm going to pull that 2 out front of the natural log. Okay, so now I have the natural log of x plus the natural log of y plus 2 times the natural log of z. Okay, so now you see that that's about as far as we can go with this problem. We used two properties in conjunction with each other. You can kind of see that this expression here is much bigger, more expanded than this one that we started with. Okay, that's why they call it expanding. All right, so let's take a look at one more example over here in number 2. If I look at this one, the first thing that I notice here, I see this fraction bar that's yelling quotient, right? This is a quotient, and that means that we're probably going to use the quotient property to expand this guy. So let's go ahead and apply the quotient property. To this logarithm. Okay, so the quotient property tells me that I can split up that quotient into a difference of two logarithms. So I'm going to say the natural log of x, right? The numerator comes first, minus the natural log of the square root of x squared plus 1. Okay, so I went from that single logarithm to two logarithms, difference of two logarithms now. Okay, now the next thing I'm going to do is I'm going to go ahead and focus on this part of our expression here. So notice again, I have a square root, and a square root is the same thing as a fractional exponent, specifically an exponent of 1/2. So I can rewrite this as the natural log of x minus the natural log, and then be careful with your parentheses here. So big parentheses, this big parentheses here, the first one that I'm writing, is to enclose everything that's going to be in the logarithmic function. Okay, the second parentheses is going to be everything that's enclosed inside of the radical. So I'm going to have x squared plus 1, and then on that, I'm going to raise that to 1/2. Right? So x squared plus 1, the quantity raised to the 1/2, is the same thing as saying the square root of x squared plus 1. And then I'm going to close parentheses on the log. Okay? Now I'm going to apply the power property. Okay? Because the power property allows me to pull exponents out of the log and put them in front. Right? So I'm going to be taking this 1/2 and moving it out front here. Okay, so what I have now is the natural log of x minus the natural log of x squared plus 1, and I'm going to put that 1/2 there. So I actually have the natural log of x minus 1/2 the natural log of x squared plus 1. And that's about as far as you can go with that one. Okay. All right, so let's take a look at a couple of examples of condensing, right? So the instructions on these two problems are a little bit different in that we're trying to compact our expression now. We're trying to rewrite it so that it's nice and compact. So we're trying to put everything together as much as we possibly can. And some of the things that you want to look for here, if you see any coefficients or any numbers in front of any log, those are actually exponents that can be put back on top of whatever's inside of that logarithm because of the power property. So that's the first thing I'm going to do here is I'm going to apply the power property and put those exponents back. So power property, okay. So I'm going to take this 2 and I'm going to put it back up here on the 8. And I'm going to take this 5 and I'm going to put it back up here on the z. So now I have the natural log of 8 squared plus the natural log of z to the 5th power. Okay. All right, that's wonderful. So the natural log of 8 squared I can say is the same thing as the natural log of 64, right? Because 8 squared is 64 plus the natural log of z to the 5th. Now notice I'm gonna circle my addition sign here, right? Whenever we see addition between two logs with the same base, that should be a big bell going off in your head saying product property, right? So we can go ahead and apply the product property and combine those two natural logs together with the product property. So what I'm going to get is the natural log, and inside I'm going to take this 64 and this z to the 5th, and I'm going to multiply those together inside of one logarithm. Okay, so what I get is the natural log of 64 times z to the 5th. Okay, and that's about as far as we can take that one. That's about as condensed as we're going to get that. Okay. All right. So let's go ahead and take a look at another one here. Number 4. This one's a big one. This one's going to require a little bit of thought. You need to be careful with the order in which you do things. Okay. Students tend to make a lot of mistakes, and it usually comes in the order that they do things. Start by getting rid of any brackets or parentheses that you can get rid of. Okay. So I'll kind of point those out to you here. So notice that we have this bracket here enclosing those two natural logs that you see inside. What I want to do is I want to start by taking this 1/2 and distributing it to each of those terms inside of the brackets. Okay, so that's exactly where I'm going to start. So I'm going to start with the distributive property. Let me kind of draw lines separating things here. So distribute. Okay, so here's what we have. We have 1/2 times the natural log of x plus 1 plus 1/2 times 2 is just 1. So I'm just going to get the natural log of x minus 1 plus 3 times the natural log of x. Okay, so I got rid of those brackets. All right, the next thing I'm going to look for is any instances of the power property that I can use. So if I see any numbers in front of any logarithms, I'm going to put those back in the exponents where they came from. Okay, so I see, for one, I see a 1/2 here. That's going to go back up into the exponent here. And I see a 3 that needs to go back up into the exponent here. Okay, so I'm going to go ahead and rewrite this after I apply the power property. So we have power property being applied. So we have the natural log, and again I need a couple of parentheses here. So I have x plus 1 raised to the 1/2, and all of that is contained inside of that natural log function, plus the natural log of x minus 1 plus the natural log of x cubed, right? And that x cubed is inside of that natural log. Okay, so we applied the power property. We've got those exponents put back. And now I see these plus signs, right? So plus signs should be saying product property, right? So I'm going to go ahead and apply the product property. Since all of those are natural logs, they all have the same base, so I can go ahead and apply that product property to them and combine those into one natural log. Okay, so I'm going to have the natural log of, and I'm going to start with this guy, right? So I'm going to have the natural log of x plus 1 raised to the 1/2 times. And I'm going to multiply that by this guy, right? What's inside of this natural log. So I'm going to need an x minus 1 times, because I have one more log to take care of here, times whatever's inside of this natural log. Okay, so now I have times x cubed, and then close parentheses on that one to make sure that everything is contained inside of that single logarithm. And this is really good right here. This is where we can stop. Okay. That one is a tricky one. I do recommend that you take some time and go and find some of these problems in section 3.3 of the book and make sure you practice them because you will see a few of these problems on the quiz and on the unit test. Okay, some other simple properties that we need to cover on logarithms. I got 4 of them here that I want to make sure I touch on and that you have as a reference in your notes. So the first one says the log base a of 1, right? So a can be any base or any number that you would like. So the log of any base of 1 equals 0. And this is because if I think about this in exponential form, we say a raised to the 0 must be 1, right? Since a to the 0 must equal 1. And that's true because we know that any number raised to the 0 is going to be 1. So if you see a 1 inside of a log, it doesn't matter what the base is, the answer is always going to be 0. Okay, and just a quick example of that, for instance, if I have a log base 3 of 1, right, it's going to equal some number. So when we say 3 raised to something equals 1, well, 3 raised to 0 equals 1, right? So that question mark is always going to be 1. All right, item number 2 here, we have log base a of a equals 1. And this is since, again, thinking about that exponential form, if I take a raised to the first power, I'm going to get a, right? Let me clean that up here. Running out of room, right? So a raised to the first should give you a, right? That makes sense. Okay, number 3, we're looking at log base a of a to the x. So we have log base a of a to the x, and this is since, let me start over here, sorry. Since, if we think about this in exponential form, I'm going to take this a, right, there's the base, I'm raising it to the x, and obviously a to the x is equal to a to the x. Okay, so it's like these two a's kind of cancel each other out, and you're left with just the x. Okay, alrighty. Well, let's take a look at number 4 here. So this one is what's called the one-to-one property. And this is going to be very handy in solving logarithmic equations. If we have a situation where we have a log base a of x equal to a log base a of y, so if I have a log expression on the left-hand side of an equal sign and a log expression on the right-hand side of the equal sign, we can, as long as they have the same base, we can take what's inside of those two logarithms. So I can take this x and I can take this y, and I can set those equal to each other. Okay, so a good example of that would be something like this. Like, let's say I have an equation log base 5 of 3x, right, is equal to log base 5 of 9. Okay, so since these two logs have the same base, I can take this 3x and this 9 and just set them equal to each other. Right? So 3x equals 9, therefore x equals 3. And voila, we just solved our first logarithmic equation. Okay? And that's by use of that one-to-one property. Okay, so 3 more quick exercises here. How can we use these properties to evaluate complicated logarithmic expressions without a calculator? This is really where their uses came in, because back in the day they didn't have calculators, so they needed to have strategies to be able to solve these things without them. Okay, so again, think about it like this. We have we typically don't like radicals in our log expressions. We like exponents, right? Because that's what a log is. It's an exponent. So I'm just going to rewrite this one real quick as log base 6 of 6 raised to the 1/3 power. Okay. So rather than saying a cubed root or a third root, I'm going to say that's the same thing as 6 to the 1/3. And set that equal to some question mark. So we're going to go ahead and we're going we're going to take this 6 and we're going to say 6 raised to something equals 6 to the 1/3, right? So 6 raised to question mark equals 6 to the 1/3. And well, since we have the same base in these exponents, we can set the exponents equal to each other. So question mark must be 1/3. And that's actually a good demonstration of property 3, right? So when we talk about property 3 here, we have log base a of a to the x. The a's kind of cancel out there and leave us with just the x. And that's exactly what happened here. These 6's kind of canceled out and we were left with the 1/3. Okay. Here in item number 2, notice right away that we have a base of 4 in each of these logs, and these two logs are being added together. So that should be screaming product property, product property. Okay, so I'm going to rewrite this using the product property. I have log base 4, and I'm going to take 2 and 32 and multiply them together inside of one log. So that's with the product property on that one. Okay, and this is obviously going to be equal to some number. We're not sure what it is yet. I can multiply that 2 and 32, so log base 4 of 64 equals question mark, and then use exponential form to finish this off, right? So 4 raised to some number equals 64, and that's going to be 3, right? We have to raise 4 to the 3rd power to get 64. All right, last one here. We have 3 times the natural log of e to the 4. So first thing I see here, I see a number out front of the natural log. So I'm thinking power property on this one, so I can put that 3 back up into the exponent. So I'm going to rewrite this as the natural log of e to the 4th raised to the 3rd. Okay, and that entire expression is inside of the natural log. So again, I see an e raised to the 4 raised to the 3rd. So this is a power to a power. So I'm going to multiply those two exponents. So what I actually get is the natural log of e to the 12th power. And this is equal to some number, right? Well, I know when I say natural log, I'm actually saying log base e of e to the 12th equals question mark. And again, if I reference property 3 from above, I know that these e's are going to cancel out, and what I'm left with is 12. So question mark equals 12. All right. That concludes the notes for section 3.3. Hopefully you found them useful.